Alrighty, in this video we're taking a look at uniform distributions. So this is continuing to look at probability distributions. In this case, we're going to have uniform distributions, meaning that all outcomes have an equal chance. Examples of when we would be looking at all outcomes have an equal chance is when we're rolling a die. If we're flipping a coin, the outcomes have an equal chance. A die, you have a 1 in 6 chance of getting 1, 2, 3, 4, 5, and 6. If flipping a coin, you have 50-50 chance of getting either heads or tails. So the probabilities are equal. So these kind of probabilities, where all the outcomes are equal, is going to give us a uniform distribution, and our probabilities are always going to be 1 over the number of outcomes. So like a die, 1 in 6, because there's 6 different outcomes. So in our example here, note the correction. I did say dice, and I probably should have said die, because I meant to do 1 singular, die, not 2. A board game has players move based on a die roll. What does the probability distribution look like? So our roll values here, we have 1, 2, 3, 4, 5, and 6 are the possible rolls. The probability of each roll is going to be 1 in 6. So each roll has a 1 in 6 chance of occurring. And then if we actually calculate out our x by p, then we have 1 over 6, 2 over 6, 3 over 6, 4 over 6, 5 over 6, and 6 over 6. So again, we're just multiplying these two values, getting those there, which we will use shortly. The next part here says sketch a graph of the probability distribution. So this is a graph of the roll value, which is our little x, compared to the probability, P capital X, and this would be, for each case, it's 1 out of 6. Probability is 1 out of 6, which is 0.166666666 repeating. So we'll say it's about 0.167 if we round that out. So we could say right here, this value is 0.167 as a decimal. So we have our rolls of 1, 2, 3, 4, 5, and 6. And then if we were to draw this out here, what we would get, if I can pick up my ruler, is a series of bars that are all exactly the same height. So we have our 1 here. Maybe I'll shade in every second one or something. There's 1, 2, 3, 4, 5, and 6. So there's our 1 bar. There's our 2 bar here. Our 3 bar, our 4 bar, and our 6 bar. So each of those bars are all going to be the same length in our histogram of the probability distribution, because they all have an equal probability. If we want to calculate the expected value, then what we need to do is sum up all of our outcomes times their probability. So that's a sum of all of these values here. So if we add all these up, we have 1 over 6 plus 2 over 6 plus 3 over 6 plus 4 over 6 plus 5 over 6 plus 6 over 6. And we're going to get, what do we got here? 3, 6, 10, 15, and 21 over 6. And if we divide that out, we're going to get 3.5. So our expected value in rolling a die is going to be 3.5. And what that means is if, as we roll the die, we would expect that at any given time, we would move 3.5 spaces in this game, which I'm assuming we're doing is moving spaces in this game that I made up. So that would be our expected value, and the meaning would be that what we would expect as a value on the die. Now remember, 3.5, we can't get 0.5 on the die. That's just overall we would expect to roll a value of 3.5. Instead of just looking at the probability and the outcome, we can actually find some usefulness of the outcome in terms of gaming by looking at if a game is fair or not. And so a game is considered fair if the expected outcome is equal to 0. So we have a game that we're going to look at here. The game uses a 4-sided die, so that means it only has the numbers 1, 2, 3, and 4 on it. If you roll a 1 or a 3, you get 3 times the rolled value. If you roll a 2 or a 4, you lose 2 times the rolled value. So is the game fair? So we should expect that the outcome of this should be 0 to be a fair game with equal chances of getting a positive finish and then equal chances of losing and getting a negative finish. So if we take a look at our rolls, we can roll a 1, 2, 3, or 4. If we roll a 1 or 3, we get 3 times the rolled value. So we get 3 times 1, we'd get 3 points. And if we got a 3, we would get 3 times 3, which is 9 points. If we rolled a 2 or a 4, we get negative 2 times that rolled value. So we'd get negative 4 points. And here we'd get negative 8 points. So now the probability of each, this is a 4-sided die. Each side of the die each number on the die has an equal chance of being rolled. So we have a 1 in 4 chance of getting a 1, a 1 in 4 chance of getting a 2, a 1 in 4 chance of getting a 3, and a 1 in 4 chance of getting a 4. So now we can do our expected value by multiplying the outcomes by the probability. So I have 3 times 1 over 4. I have negative 4 times 1 over 4. 9 times 1 over 4, and negative 8 times 1 over 4. So to find the expected value, we have to sum all these up. So we have 3 plus negative 4, that's negative 1. Negative 1 plus 9 is going to give us 8. 8 minus 8 is 0. We get a result of 0 over 4. And so in this case, with a result of 0 over 4, that is equal to 0. So this game would be considered fair. If you want to take a look at an example of a game that is not fair, if you look at page 156 in the textbook, example 2 on fair games, you can take a look at that one, and that has you rolling a 6-sided die in a similar type of game. And you end up getting a negative result. On average, a player would lose points in that game. And so that would give you a good example of a case where someone would actually lose in their game versus win. So moving or to help out with some of the types of questions we're doing, especially since like you look at the die from the first question where we ended up taking our situations, adding 1, 2, 3, 4, 5, and 6. Just a kind of additional useful tool in terms of working with expectations. A lot of times you can sum numbers 1 to n quickly by using the formula n times n plus 1 over 2. So that's the mathematical full formula, but all you do if you want to add the numbers 1 to 10, we could do 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. A little easier way to do it is 10 times 11, okay, 10 plus the next number divided by 2, and that'll give you 110 divided by 2, and that's going to give you 55. So the numbers 1 to 10 would add up to 55. You can do this with any pair of numbers or any series of numbers as long as you're starting at 1 and adding all the way up to that number. You take the last number, multiply it by the next number, divide by 2, and it'll work out. We did do this proof in class as well during our first or second unit.